A small piece of uranium, the size of a grape, can produce enough energy to power an entire neighborhood for an entire year. But how can such a tiny amount pack such a powerful punch? To find out, let's dive into the factories responsible for producing and processing the world's most dangerous metal and explore its incredible journey together. The history of enriched uranium is closely linked to the birth of nuclear energy. In 1896, French physicist Henri Becquerel discovered radioactivity by observing that uranium spontaneously emitted radiation. This discovery inspired Marie and Pierre Curie, who isolated elements such as radium and polonium. In 1932, James Chadwick discovered the neutron, a fundamental particle for nuclear fission. Then, in 1938, Otto Hahn and Fritz Strassmann, with the collaboration of Lise Meitner and Otto Frisch, demonstrated that a uranium atom could split when struck by neutrons, releasing a colossal amount of energy. Enriched uranium, essential for controlled fission, represented a major technological challenge. Natural uranium contains approximately 99.3% uranium-238, which is difficult to split, and only 0.7% uranium-235, which is perfectly suited to fission. Increasing the proportion of uranium-235, a process called enrichment, proved essential for both nuclear reactors and atomic weapons. During World War II, as part of the Manhattan Project, scientists developed the first enrichment methods. Gaseous diffusion used porous membranes to separate uranium hexafluoride gas, while electromagnetic separation used magnetic fields to deflect the isotopes. These processes were slow and energy-intensive. In the 1950s, gas centrifuges revolutionized production. These machines, spinning at breakneck speeds, separated isotopes by mass in a much more efficient and compact manner. Their design was so strategic that their plans were classified as a state secret. In 1951, the experimental Brettair Reactor 1 reactor at IDEO used enriched uranium to generate electricity for the first time, lighting 4 light bulbs. 3 years later, in 1954, the Obninsk power plant in the Soviet Union became the first to connect nuclear power to the electricity grid using uranium enriched to 5%. Today, enriched uranium fuels reactors that generate approximately 10% of the world's electricity. But how can this element produce so much energy? The journey begins in uranium mines, located in remote areas such as the Australian desert, the steppes of Kazakhstan, or the rock formations of Canada, which together provide nearly 70% of the world's production. Uranium is present in minerals such as peach or uranite, often in low concentrations, between 0.1% and 2%. Operations can be open pit, where huge excavators remove the earth, or underground, with galleries extending several hundred meters down. In some cases, in situ leaching is used. Chemical solutions, such as sulfuric acid or carbonates, are injected into the deep layers to dissolve the uranium, which is then pumped to the surface. The extracted or is transported to processing plants, where it is ground into a fine powder, similar to coarse sand, to facilitate separation. It is then mixed with acids or bases in large steel tanks. This process isolates uranium from other elements, such as iron or quartz. The resulting product is a bright yellow powder called Yellowcake, or uranium oxide, containing approximately 80% pure uranium. This material, which is weakly radioactive but toxic if inhaled, requires protective equipment, masks, and sophisticated ventilation system. A single ton of this Yellowcake can provide as much energy as several million tons of coal. It is then shipped to conversion plants, where it is transformed into uranium hexafluoride, a gaseous compound at moderate temperatures, ideal for enrichment. The process begins by purifying the Yellowcake to remove impurities such as sulfur, magnesium, and other metals. This step takes place in corrosion-resistant stainless steel tanks. The purified uranium is mixed with hydrofluoric acid and then heated in sealed reactors. It transforms into uranium hexafluoride, a volatile compound that transforms from solid to gaseous at around 56 degrees Celsius. It is then stored in cylindrical steel containers specially designed to withstand its corrosive nature, as it reacts violently with water. Conversion plants are governed by strict safety standards and feature advanced ventilation systems and highly sensitive leak detectors. At room temperature, uranium hexafluoride can crystallize into a fine green powder nicknamed nuclear snow because of its texture and color, although handling requires specialized equipment. The next step, enrichment, aims to increase the proportion of uranium-235 to about 5% for civilian use. Gas centrifuges, a true marvel of engineering, perform this task. Made from special steels or carbon fiber composites, they rotate at over 50,000 revolutions per minute in vacuum chambers. Uranium hexafluoride gas is injected into them. Centrifugal force separates the isotopes, with the lightest, uranium-235, concentrating in the center, while the heaviest, uranium-238, is expelled to the outside. The uranium-235 enriched gas is then collected separately. The centrifuges operate in cascades, that is, in a series of hundreds or thousands of interconnected machines. Each refines the mixture a little further until it reaches the desired level of enrichment. These installations are surprisingly quiet. Only the slightest vibrations due to rotation are perceptible. The slightest imbalance, even a few milligrams, could damage them, hence the constant monitoring by sensors and automatic systems. A modern centrifuge can process several tons of uranium gas each year. The most recent complexes, particularly in Europe, house cascades capable of operating continuously for decades. The enriched gas is then converted back into solid uranium oxide through controlled chemical reactions. This new oxide, ground into a fine powder, is pressed into molds to form small cylindrical pellets about 1 centimeter in diameter and weighing 7 grams each. They are then fired in ovens at about 1,400 degrees Celsius to produce a very dense material capable of withstanding the heat and radioactivity of the reactor core. Each pellet undergoes rigorous quality controls. X-rays detect microcracks, lasers verify dimensions, and chemical analyses ensure the absence of impurities such as boron or carbon. A single one of these pellets releases as much energy as a ton of coal. They are inserted into long tubes made of zirconium, a silvery metal that is corrosion-resistant and transparent to neutrons, a property essential for fission. Each fuel rod, approximately 4 meters long, contains nearly 400 pellets stacked with millimeter precision. The rods are assembled into clusters, called fuel assemblies, comprising several dozen rods fixed in metal structures made of robust alloys, such as stainless steel or cercolois. A single assembly weighs approximately 500 kilograms and requires more than 100,000 welds, each verified by ultrasound. The internal grids are designed with precise geometric patterns to optimize the flow of neutrons and coolant. Before shipment, these assemblies undergo extensive testing, including ultra-precise weighing and vibration, simulating reactor conditions, ultrasonic inspections, chemical analyses, and pressure tests. A single assembly can produce enough electricity to power 100 homes for a year. At this stage, the radioactivity remains low. Technicians can handle them with simple gloves and filter masks. In the nuclear power plant, the assemblies are placed in the reactor core, where fission is activated. A typical reactor contains about 480 assemblies, or nearly 5,760 fuel rods, enough to power an entire small city. During fission, the atoms of uranium-235 split under the impact of neutrons, releasing heat and new neutrons that sustain the chain reaction. The energy released by a single atom is millions of times greater than that released by a burned carbon atom. To control this reaction, regulation rods made of boron or cadmium absorb some of the neutrons. The reactor core is protected by thick, 2-meter-high reinforced concrete walls designed to withstand earthquakes, floods, or even a plane crash. Automated systems continuously monitor temperature, pressure, and neutron flux, immediately shutting down the reactor at the slightest abnormal signal. The heat from fission is used to convert water into high-pressure steam, which drives huge turbines spinning at about 1,800 revolutions per minute. These turbines are connected to a generator that converts the motion into electricity. A single reactor can produce over 750 megawatts, enough to power 500,000 homes, the equivalent of a large city. Unlike coal-fired power plants, nuclear power plants emit almost no carbon dioxide, yet they provide continuous energy production. This characteristic makes them an essential tool for the global energy transition. After approximately a year of operation, the fuel rods are removed, their energy having been almost completely released. However, they remain extremely hot and radioactive. They are therefore manipulated remotely by robotic arms, then immersed in cooling pools located within the power plants themselves. These pools, approximately 8 meters deep and filled with ultra-pure water, serve as both a shield and a cooling system. The water is constantly filtered and monitored to detect the slightest variation in temperature or radioactivity. The rods remain in the water for about 10 years, allowing their heat and radioactivity to significantly diminish. Some power plants store more than 700,000 spent rods, an impressive volume, but one that would fit in a medium-sized warehouse. Fascinating fact, these pools sometimes emit a faint blue glow, known as the Cherenkov effect, caused by particles moving faster than light in the water, a spectacular but harmless phenomenon. After several years, the cooled fuel is transferred into dry steel and concrete containers capable of preserving it for centuries. These containers, stored in secure locations, are resistant to shocks, weather, and natural disasters. Long-term nuclear waste management remains a major research topic. Scientists are working on deep geological repositories located more than 500 meters underground in stable rock formations, such as granite or salt, to permanently isolate waste. Projects such as Yucca Mountain in the United States or Onkalo in Finland are designed to remain safe for at least 10 millennia. Nuclear energy thus remains one of the most promising solutions for a sustainable future. Despite the prejudices, this technology now meets very strict safety standards and produces little waste compared to other industries. Moreover, it provides continuous electricity with almost no carbon emissions, making it a crucial ally in the fight against climate change. With continued investment in research and development, nuclear energy could continue to light our world in a clean, safe, and reliable way. And that's how enriched uranium is made. What do you think? Share your thoughts in the comments. If you like this documentary, don't forget to like, subscribe, and hit the bell to never miss any of our content. But don't leave yet, that's not all. The rest of this video will be just as fascinating, so stay with us until the end. How do thousands of gold bars come to life in a factory? Gold, the ultimate precious metal, is a timeless symbol of wealth, power, and elegance. From raw to gleaming bars, the transformation journey is far more complex and perilous than it seems. Since their discovery several millennia ago, methods for refining and manufacturing ingots have continued to evolve and improve. In the past, rudimentary techniques based on melting and casting were used. Today, modern technology has made it possible to achieve unprecedented levels of purity and precision. Fascinating mankind for over 5,000 years, gold held a sacred place among the Egyptians, who considered it divine flesh, while the Roman Empire made it a standard of power by minting its coins. However, the concept of a standardized ingot as we know it today only emerged between the late 19th and early 20th centuries, when governments and central banks decided to store their reserves in the form of uniform gold bars. A gold ingot, or bar, refers to a mass of refined gold manufactured to precise shapes and specifications. Its production takes place within a strict framework where every detail, from labeling to registration, is meticulously controlled. The London Bullion Market Association sets the rules to ensure each bar meets strict criteria for weight, size, and purity. So how is a gold bar actually made? The process is extremely sophisticated and requires cutting-edge equipment, advanced chemical expertise, and high-level technical know-how to transform raw or into dazzling bars. It all starts with extraction. Gold is buried in the Earth's crust, often mixed with quartz or various sulfides. The extraction method depends on the nature and depth of the deposit. Open pit mining is preferred for deposits close to the surface. It involves removing thick layers of earth and rock, called overburden, to expose the gold-bearing ore. Gigantic machines, such as hydraulic excavators and powerful haul trucks, extract and transport impressive quantities of material. Once extracted, the ores are transported, either by truck or conveyor, to processing sites. These open-pit mining operations are on a colossal scale. Some operations move several tons of ore every day. Safety requires extensive geological studies and continuous monitoring to ensure the stability of the quarries. This method offers high yields, making it ideal for shallow deposits. Underground mining, on the other hand, is used to reach deeper veins. It involves digging vertical shafts and galleries to follow the gold veins. Techniques such as drilling or blasting break up the rock, which is then transported to the surface using conveyors or conveyor systems. In this type of mine, safety is paramount. Seismic sensors, reinforced supports, and ventilation systems protect workers from collapses or accidents. Once extracted, the ore is immediately crushed to reduce its size and facilitate transport to the plant. Crushing and grinding then follow. The raw ore must be prepared before beginning the extraction process. Initially, jaw or gyratory crushers reduce the rock blocks into more manageable fragments. These phases, often in 2 stages, first divide the ore into gravel-like pieces, before secondary crushing further reduces the size to make it suitable for grinding. Grinding, carried out in huge ball or semi-autogenous (SAG) mills, pulverizes the ore into a fine powder. The heavy steel balls or bars rotating in these machines break the rock using kinetic energy. To enhance the process, water is added, creating a fluid pulp. Sophisticated sensors ensure continuous control of the particle size, optimizing energy consumption and maximizing gold recovery. Next comes separation and concentration. This step aims to isolate the gold from unnecessary minerals. Several techniques are used. Gravimetric separation relies on the high density of gold, which distinguishes it from lighter particles. Shaking tables and spiral concentrators separate the heavy elements from the waste. While highly effective for coarse particles, this method becomes less effective for fine particles, requiring additional processes. Flotation is a more advanced method. It involves introducing chemical reagents that make the gold hydrophobic. An injection of air bubbles then carries the gold to the surface, fixed on the scum, where it is recovered. This process, highly dependent on chemistry, ensures an excellent yield for microscopic gold. Cyanidation, on the other hand, is one of the most widespread techniques. By mixing the ore pulp with a cyanide solution, the gold forms a soluble compound. It is then recovered by precipitation, using powdered zinc or activated carbon, producing a gold-rich concentrate. Once this concentrate is obtained, it moves on to the smelting and refining stage. Heated to over 1,200 degrees Celsius in specialized furnaces, and melt it with fluxes such as borax, which trap impurities in the form of slag. The molten gold, now separated from the waste, is poured into molds to form semi-pure bars. The final refining achieves exceptional purity. 2 processes dominate: electrolysis and orgal. Electrolysis dissolves gold in a gold chloride solution, redepositing it in pure form on cathodes. Orgal, a mixture of nitric and hydrochloric acid, dissolves the gold before it is filtered and remelted. These methods result in gold of 99.99% purity, meeting world standards. The purified gold is then remelted in induction furnaces and then poured into molds calibrated to international standards, including the London Good Delivery Bar. Cooling is achieved by immersion in water or exposure to air, ensuring perfect solidification. More and more factories are using robotics to handle the hot molds, reducing risks and improving productivity. After demolding, each bar is carefully inspected for any imperfections. Shaping and engraving then follow. Automated machines correct excess material and polish the contours. Next, a laser engraving inscribes key information: weight, purity, refinery logo, and serial number. Some ingots even feature micro-engravings invisible to the naked eye, serving as protection against counterfeiting. Each ingot undergoes rigorous quality control. X-ray fluorescence or spectrometry analyses verify purity, while digital measuring tools control dimensions. Conforming bars are packaged under tamper-evident seals and accompanied by a certificate of authenticity. Thus, each ingot leaving the factory is a piece of engineering and craftsmanship ready to be integrated into the vaults, reserves, or portfolios of investors around the world. But these factories, beyond their image of prosperity, are also high-risk places. Huge quantities of gold attract covetousness, and security is at its highest. Armed guards, cameras, ultra-reinforced safes, and biometric checks screen every employee. Transport is carried out in escorted armored vehicles equipped with GPS and advanced protection. At the same time, danger is ever present for the workers. Extreme heat from the furnaces, toxic chemicals, and gigantic machines capable of causing serious accidents. Every move must be executed with pinpoint precision. And most importantly, don't forget to like, subscribe, and hit the bell so you don't miss any of our upcoming content.